All right, we're recording now. And our sponsor is stamps.com. Okay. So yeah, any questions before we get started? Awesome. So we are going to keep going, just working through some examples of taking the inverse Z transform. I'm going to try to get through all of that today, although we may not, in which case we'll pick it up on Monday. So just to recap, the salient bits of taking the inverse Z transform are these guys, right? If M is less than N, then the Z transform breaks down to this guy, that X of Z is equal to the series from K equals 1 to N of A of K, which is some rando constant, over 1 minus D sub K times Z to the negative 1. Then you break it all out and you got to solve for A sub K using this formula, and it's pretty straightforward. Any questions about how to do that? Like I said, it gets a little unwieldy, as we saw. It gets kind of messy and kind of strange, but fundamentally the math is pretty easy. So let us do an example of, now, what happens if it's the other way around? If M is greater than or equal to N. And here it gets kind of weird. The formulas get kind of strange. So what we have to do is this. We're going to start with this form of our inverse Z transform. X of Z is equal to the series from R, we use lowercase r equals 0, to M minus N of B sub R times Z to the negative R, plus our thing from before, the series from K equals 1 to N of A of K over 1 minus D sub K times Z to the negative 1, right? So this part will be exactly the same as it was before, right? We're going to break it out, we're going to solve for A of K, we're going to get our stuff. But what makes it strange is we got to find now this business. And we got to find it first so that we can use it in the formula for A of K. So let's just jump in and do an example. So let's say that we've got a Z transform that is this ugly dude. We got X of Z is equal to 1 plus 2 times Z to the negative 1 plus Z to the negative 2 over 1 minus 3 halves times Z to the negative 1 plus 1 half Z to the negative 2. So if you do a little algebra and you sort of factor this out, it will factor down to this. X of Z equals 1 plus Z to the negative 1 squared over 1 minus 1 half Z to the negative 1 times 1 plus Z to the negative 1. Right? All we did was algebraically factor out those two expressions. All right. So what we have here is there are two zeros and two poles, right? So there are two zeros at what, Z equals negative 1, and a pole at Z equals 1 half, and also at Z equals negative 1. Very strange. Okay. But that's not important now. What matters is that M is equal to Z, the number of poles and the number of zeros. Or M is equal to N. The number of poles and the number of zeros is the same. So we're going to rearrange it and put it in that form that we can use to get our by inspection solution. So since they're equal, remember here that we had the series from M, from R equals 0 to M minus N. So that's going to be 0 since they are the same, which means we'll only have one term over here, B sub 0, plus A1 over 1 minus 1 half Z to the negative 1 plus A2 1 minus z to the negative 1. Did I mess that up? I did. That should be negative. Which makes sense since that's a positive right there. Okay, I apologize. So, quick change the notes right there. That should be 1 minus z to the negative 1, which would put that 0 at positive 1, or put that pole at positive 1, not negative 1. That should have been the red flag when the pole and the 0 are the same place. All right. So let's see. We got to find b of 0. And to find b of 0, we use this weird kind of long division method. B of 0 is found using long division. In fact, they'll all be used or found using long division. And what I mean by that is we're going to do b of 0 is equal to this expression that we'll unpack here in a second. 1/2 z to the negative 2 minus 3/2 z to the negative 1 plus 1. That is the denominator divided by the numerator, z to the negative 2. And we've rearranged it to put the higher order z's up front. Bring that down to give us some more room. Okay. So, to find b sub 0, just to recap on that, we're going to take our original expression and we're just going to do the division, right? We're going to do this guy, the numerator divided by the denominator, and what's left over is going to be our b of 0. So let's take a look at what that looks like. Does anyone know how to do long division with a weird looking polynomial like this?
I think in algebra 2, like back in school, when I did, but I definitely don't remember now.
Then you multiply the whole part on the left by like a, I guess a z in this case.
Exactly, yeah. So what you're going to do, well, not by a z necessarily. What you're going to do is you're going to put a term. All you really care about is this. You want to put something here that's going to multiply with that to give you 0. You want to eliminate the first term, right? That's really all you care about. You can ignore pretty much everything else in the expression except for the very first term. And so what we want to do here, like I'll just keep it in pink, is we only care about matching 1/2 z to the negative 2 with z to the negative 2. So how do we do that? Multiply by 2, yeah. So it'll be 2, which means that we'll get what? So we'll get 2 z to the negative 2 minus, so now it's here, minus 3/2 times 2 is going to be, what, minus 3 z to the negative 1 plus 2. And we subtract them. We're going to get 0. 2 minus negative 3, so it's going to be 5. Z to the minus 1. And then 1 minus 2 is minus 1. So let's see. Now we've reached a point where we have our remainder here that is a lower order than this. So that's z to the negative 2. That's z to the negative 1. We don't want to put any z's up here, right? Because this is supposed to be a constant. So we're done, essentially. That's the end of the story. So this is what's left over, which means that our new x of z is equal to 2 plus the remainder, 5z to the negative 1 minus 1 over all that stuff. 1 minus 1/2 is z to the negative 1. 1 minus z to the negative 1. Cool. So that's how you get rid of that b sub 0. Did we mess up negatives? I don't think so, Akil.
No.
I don't think, yeah, no, I think I'm good. Oh, people are
You
typing
might,
aggressively.
put parentheses at the beginning and end of what you're dividing by. Because you're subtracting the whole term, right? So that might be what's tripping people up.
Wait, put parentheses where?
So in the pink, you have
Yeah.
the negative out front of the first term.
Oh, yeah.
It applies to everything, right?
Yeah, so it's negative all of that. So we're subtracting that stuff. That's a good catch, man. Is that what we were talking about, guys? Yeah, we're not multiplying by negative one, we're just subtracting one from the other. Okay. Oop, you're right. And somebody else pointed out 2 times 1/2 is 1. So that 2 needs to go away. Good job, Andres. And that subtracts to 0. So that happens when I just like blindly follow my notes without actually paying attention to what I'm doing. All right. So any questions about how we got our b sub 0? Okay, now we do the a sub 1 and a sub 2. Using the same formula that we had before. So we're going to hunt for a sub 1. So that a sub 1 is equal to this whole big monster. 2 plus 5z negative 1 minus 1 over all of that business. 1 minus 1/2 z to the negative 1. 1 minus z to the negative 1 times 1 minus 1/2 z to the negative 1. All of that evaluated at z equals 1/2. So that is a disgusting expression, but that's just an interpretation of what we had. Let's see. Coming back up here, a of k is equal to the denominator that we're sort of accounting for times x of z, right? And we just found out x of z is this whole big monster. So that's what we're doing here, and the whole thing is evaluated at z equals 1/2. So let's take a look. So we got a1 is equal to, I'm just going to distribute, so it'll be 2 times 1 minus 1/2 z to the negative 1 plus 5z to the negative 1 minus 1 times 1 minus 1/2 z to the negative 1 over 1 minus 1/2 z to the negative 1. If you're the kind of person that just really enjoys doing lots of long algebra, then you have come to the right place. All right, so let's see, a couple of things are going to happen. First off, most importantly, these guys will cancel each other out. And then we'll go ahead and apply the z equals negative 1. So we'll say a1 is equal to 2 times 1 minus 1/2 times 2 plus 5 times 2 minus 1 over 1 minus 2. Don't forget, yeah, z, 1/2 to the minus 1 is 2. That's what we're doing here. And so let's see, this is going to get us 2 times 1 minus 1, which is going to go to 0, plus what? 10 minus 1 over negative 1. That's going to go to 0, so we're going to get that a1 is equal to 10 minus 1 is 9 over negative 1 is just equal to negative 9. a1 is equal to negative 9. Any questions about that one? Give me a second to finish, jot it down. A2 is going to work out in about the exact same way. A2 equals, again, this big long expression, 2 plus 5z to the negative 1 minus 1 over 1 minus 1 half times z to the negative 1 plus 1 minus z to the negative 1 times, now it's the other one, 1 minus z to the negative 1. Now we're doing z equals negative 1. Not negative 1, positive 1. Boop. All right. So now we just do the algebra. So it's 4, 1 minus z to the negative 1 plus 5z to the negative 1 minus 1, 1 minus z to the negative 1 over 1 minus 1 half z to the negative 1, 1 minus z to the negative 1. All of that evaluated at z equals 1. So A2 is equal to 2 times 1 minus 1, which is going to go to 0 again. These guys will cancel, so we'll just get 5 times 1 minus 1 over 1 minus 1 half times 1. That goes to 0. A2 is then equal to what? 4 over 1 minus 1 half, which is equal to 4 over 1 half, which is equal to 8. So therefore, A2 is equal to 8. And our entire now simplified z transform expression here is 2 plus negative 9 over 1 minus 1 half z to the negative 1 plus 8 over 1 minus z to the negative 1. And that's the hard part. Next up, we just do the by inspection. And we're going to get that our discrete time signal x of n, the 2 by inspection, if there's no steps or anything like that, is just the impulse sequence, the sample sequence. So it's going to be 2 times delta n minus 9 times 1 half n times u to the n plus 8 times 1 to the n, but it's just 1, so 8 times u to the n. And there we go. And there we have it. So that is the partial fraction expansion method. Hopefully, you see, it's not like it's long, it's kind of tedious, but no one step is all that complicated. And as long as you just sort of, take your time, relax a little bit, just work it out, you should be able to do it without too much issue. Any questions about that?
Sound like Dr. Bernoussi. It's just simple
Simple
algebra.
algebra.
It's just simple algebra, man, yeah. No problem. No problems. All right. Any last questions before we move on to the power series expansion? All right, so that third method for taking the inverse is inverse Z transformed by power series expansion. Conveniently, the Z transform of x of n is already given to us as a power series. Probably going to find here that power series expansion method is a little bit underwhelming. It has a name like power series expansion. We just did this partial fraction expansion, which involved a whole bunch of stuff, and so you're thinking like, oh dang, power series expansion is going to be weird. It's actually kind of dumb, but pretty elegant. So x of z is already given to us as this, right? The bilateral sequence, n equals negative infinity to positive infinity, x of n to the negative n, right? Which means that, let me use green, that if we were to expand everything out, right, x of z would be equal to, you know, some stuff plus, let's say like x to the negative 2 times z squared plus x to the negative 1 times z plus x of 0 by itself. That's going to be important. Plus x of 1 times z to the negative 1, right? And so on and so forth. And basically, the power series expansion method is it's the brute force method. It's the like, well, let's just look at it and see what we get sort of method. Because if we have all this, then we just know what our terms are automatically. So for example, let's say that x of z is equal to this. Z squared times, it's even these same terms as before, 1/2, 1 minus 1/2 z to the negative 1, plus 1 plus z to the negative 1 times 1 minus z to the negative 1. The thing you should notice here is that this is a z transform that has no poles. It only has zeros. So all we do to find this one is we're going to just distribute everything out. Again, it's just simple algebra, right? Distribute everything out. So, yeah, man, let's do it. X of z is equal to, I'll just do the sort of first bit here. That gets us z squared minus 1/2 z to the negative 1 times z squared times 1 plus z to the negative 1, 1 minus z to the negative 1. Let's see, it's going to simplify to z squared minus 1/2 z minus 1. Z to the minus 1 times z squared is just z. So it's that times 1 plus z to the minus 1 times 1 minus z to the minus 1. Let's do these guys next. So we'll leave this side alone. And that's going to get us what? 1 minus z to the negative 1 plus z to the negative 1 minus z to the negative 2. Z squared minus 1/2 z times 1 minus z to the negative 2. And if we factor these guys out, or distribute them, we're going to have what? Z, I don't even need parentheses anymore. Z squared minus z squared times z to the negative 2 minus 1/2 z plus 1/2 z to the negative 1. So all I have to say, we distribute everything out, and we get x of z is equal to this. Z squared minus 1 minus 1/2 z plus 1/2 z to the negative 1. which looks eerily similar to this thing, right? Where we sort of broke it all out the long form way. So what that means is first we got to rearrange just a smidge. So x of z, want everything kind of nice in order. So z squared minus 1/2 z minus 1 plus 1/2 z to the negative 1, which means that that is our x to the negative 2. That is our x negative 1. That's our x of 0. That's our x 1. Just like that. We can say that x of n is equal to, let's see, 1 when n is equal to negative 2, minus 1/2 when n is equal to negative 1, minus 1 when n is equal to 0, 1/2 when n is equal to 1, and 0 otherwise, everywhere else. So another way to write that would be x of n is equal to what? Delta n plus 2 minus 1/2 delta n plus 1 minus delta n plus 1/2 delta n minus 1. And there you go, man. So that way it's pretty easy. You just distribute, if you've got a z transform that has no poles, right, has no denominator, or maybe a denominator that can be easily sort of hashed out, you just distribute everything until you get it all in one sort of nice, neat expression, and then you have your transform. Like I said, there's really not a whole lot to it. It's just sort of the long and tedious way. Okay. So, it's not always as easy though. Let's do another example, because sometimes what the series expansion isn't always quite so obvious. Let's say, for example, that we have x of z is equal to log 1 plus a times z to the negative 1. We say that the region of convergence is z has to be greater than a. So here's a sequence that's got some weird stuff going on to it. Who remembers Taylor series from Cal 2? There's a thing, it happened.
It happened, don't remember much of it.
It happened, go back to.
I don't remember anything else.
What's that? Well, all you really need to remember is that to find a Taylor series expansion, you just go and find the Taylor series expansion table, and you say, for log it's this, or for sine it's this, or for e raised to something it's this, so on and so forth. So the Taylor series expansion, I legitimately went and got my calculus textbook from undergrad and opened it up, and it was right here. The Taylor series expansion see, this stuff is useful, man. They didn't teach it to you just for fun. Of log of 1 plus x is equal to the series n equals 1 to infinity of negative 1 n to the minus 1 times x of n over n. Which means that, notice there's no z's happening here. That means that this is x of z is going to be equal to the series from n equals 1 to infinity of minus 1 to the n minus 1 times a to the n, or excuse me, z to the negative n, right, because that's your whole x is wrapped up in there, over n. So we're good with that part, and that was the magical part. This next part's pretty lame. All right. So remember, just like before, in the series, in the power series expansion, what our discrete time signal is, our x of n, is just everything that isn't attached to z. So that means that our x of n is equal to, let's see, minus 1 to the n minus n minus 1 times a to the n over n for n greater than or equal to 1, and 0 for n less than 1. That's all there is to it. So the punchline there is dust off your calculus textbook, find the Taylor series expansion for whatever the thing is that you're looking for, drop it in, and separate out the x, and everything that's not the x, but the z, everything that's not the z is going to be what gets transformed. Oh, sold your calculus book. Don't do that, man. It's a good book. All right, any questions about that?
There you go.
What?
He said, that's how I make some of my old textbooks to buy that computer.
There you go, man. That's the wrong message. That's not the take home. All right, let's do one last thing before we call it a weekend. Is we can do power series expansion by long division. It's got a lot of big words in it, man. Power series expansion by long division. So let's start with something that we actually already know the answer to. X of z is equal to 1 over 1 minus a z to the negative 1, and it's got to be that z is greater than a. Now we already know by inspection that x of n is equal to a of n times u of n, or a to the n times u of n. So this gives us a place to start for it, right? I'll get ahead of the question that I always get, which is, well, if we already know what it is by inspection, why do we use the inspection? Because that's not the point of the example. The point of the example is we already know what the answer is, so we'll see how did we come by this. So what's going to happen is we're just going to do the long division, right? So we'll have, 1 divided by 1 minus a to the z minus 1. Let me draw a little better. So the first thing we know is, like, we just pay attention to the first terms, right? We ignore everything else. So to get 1 and 1, well, we're just going to multiply by 1, and that's going to get us 1 minus az to the negative 1. And then we will subtract, and that will get us 0 and negative a z to the minus 1. All right, so now how do we get negative a z to the negative 1? From 1. Remember, we're always looking at our first term. So that means we're going to multiply by what? We're going to do plus a z to the negative 1. And that's going to get us az, which that should be positive, az to the negative 1, minus, what, a squared z to the negative 2, since we're multiplying everything through. Yeah. All right. And then we subtract. That'll give us 0, and then we'll have a squared z to the negative 2. And then we'll do what? We'll do plus a squared z to the negative 2. And we're just going to do this division forever and ever and ever, right? So what would this be? This would be minus a cubed z to the negative 3. So on and so forth. So we can see that 1 over 1 minus a z to the negative 1 is equal to 1 plus a z to the negative 1 plus a squared z to the negative 2 plus, a3 times z to the negative 3. So what does that mean for us? Well, that means we're going to have what? It's going to be a series from, let's say, k equals 1 to infinity, or not 1, but 0. Oop. How's it going? Not yet, we still got 3 minutes. If you want to hang out, that's cool. All right. So, what's going to go inside this series? It's going to be what? A to the k times z to the negative k? Yeah. All right. And as we just talked about, our x of n is going to come from everything that's not attached to z. So it's that. So that means that it's just going to be equal to x of n is equal to, a to the n if n is greater than or equal to 0, or 0 if n is less than 0. And another way to write that is x of n is equal to a of n times u of n. So basically there's 3 take-home bits here. There is, when you're doing the power series expansion method, the first thing is, can you distribute everything out? And if you can, that's awesome, because then you basically have all your answers, and everything is just this sort of piecemeal thing of sample sequences. Or maybe it's a weird expression, but it's something that you can look up in the table, right? And then find it that way. Or if nothing else works, you actually just work out the division until you've pieced together what the pattern is, and then you've got your solution there. Cool. That is the power series expansion method. That is it for methods and techniques for finding the inverse Z transform. Cool. Any questions, comments, concerns? All right. In that case, that is it. Be on the lookout. I'll probably post a homework assignment for doing the inverse Z transform sometime over the weekend, but it won't be due until like Wednesday or so. Yeah, and I guess I need to come up with a new Python project for you guys. So we'll do something next week. All right, anything else? Questions? What you guys in the Discord? Everybody good? All right, in that case, thank you so much. Have a good weekend. Be safe. I'll see you guys all on Monday.